Hi there. My name is Beeman. I'm the chair of the Performance Analysis SIG. I work for Rivos. I'm here with my frequent co-conspirator, Atish. We're going to talk about a bunch of the work that's been done in the community to enhance RISC-V performance analysis infrastructure. Okay, so going back to last year, back in April, we started the Performance Analysis Special Interest Group. At that time, within the ISA, there was some basic capabilities for doing performance analysis on RISC-V CPUs. We had the two counter extensions, ZI counter, which is the three M-cycle instret and M-time counters, as well as the ZI HPM, which is the programmable counters. And then recently ratified was the SSCOF PMF extension, which provides support to the programmable counters for filtering by privilege mode and taking interrupts on overflow. So some basic sampling support. We also had an SBI interface for all of that. So you could discover and configure your counters. You could start and stop them. First thing we did within the SIG was do a gap analysis, look at both from an ISA perspective as well as from software tools, enabling, et cetera, where were the gaps. And we came up with a long list, but I'm showing here what were some of our top priority gaps. I'm not going to read these to you now because we're going to go through each one through the slides here. So let's jump in. First one is looking at security and isolation concerns. So in particular, the cycle and instret counters were part of the ABI, so Linux would expose those to user code, and the problem with that is that they counted throughout all modes. So you'd see counts of cycles or instructions retired that were from privileged software execution that we really didn't want to expose to user code. And what we found was not only is that kind of leaked data, but there are deterministic side channels available as a result. So we took a twofold approach to this. One, we came up with an ISA extension. This is the cycle and instret privilege mode filtering extension. And basically what it does is a very simple fast track extension that takes the privilege mode filtering components from the SSCOF PMS extension that were applied only to the programmable counters and makes them available for the cycle and instret counters. So now if you're going to expose those counters to user mode, you can set them up to count only user mode instructions, user mode cycles, and eliminate that data leak. Further, we made some changes to the kernel such that now user access to those counters goes through perf, much the same way as done for other architectures, to further patch that leak. Okay, another issue we ran into was just having high profiling overhead. We had this counter infrastructure, but it was only writable from machine mode. And so if you have supervisor software, like say Linux perf, that expects to be able to configure and write these counters, then you ran into cases where you're having to perform e-calls into M mode to do those writes, which results in a lot of traps and a lot of overhead. If it was just when you initially set up a counter and have to take a trap there, maybe that's not such a big deal, but once you factor in that you need to be able to write counters every time you collect a sample, which, a typical rate would be every millisecond or so. Also, every time you context switch, you've got to save all the counters, at least those that are in use, and restore them. Now you're starting to talk about a meaningful amount of overhead. So once again, we looked to ISA to address this issue. We came up with the supervisor counter delegation ISA extension. What this does is essentially allow M mode to opt into selecting counters that can be accessed or written even directly by supervisor mode. That motivated creating yet another ISA extension, which is the indirect CSR access. And basically this, I'm not going to talk in detail about it because it was kind of just a means of achieving what we needed to achieve. But it takes the indirect CSR mechanism that existed as part of AIA, generalized it for use by other extensions so that we didn't consume so much of the limited direct CSR address space. So this supervisor counter delegation extension uses that, and now we have the ability for supervisor mode to directly write counters. Okay, I'm jumping onto the software side here, so I'm going to hand the mic to Atish and the clicker.
Thanks, Beeman. So looking at the high profiling overhead, The other area where profiling really costs us is when you run perf inside a guest. Now, when you run perf inside a guest, especially like a hypervisor like KVM, we rely on counter virtualization to enable easy VM migrations and also simultaneous uses of the counters both by the guest and host, because KVM also has the running in the host has the user space that can leverage perf. Now, the bottleneck there is every time you try to do counter virtualization, you have to use you cannot use the counter delegation anymore, because the hypervisor has to be aware of what guest is using. And also you have to, whenever the guest accesses those counter, we need to trap and emulate those counter accesses. So it ends up even incurring even more traps. So one way to reduce those traps is to allow those counter read access to be shared as like a snapshot of values that can be shared by the hypervisor to the guest. So that's what the SBI extension was enhanced to do the bulk mode counter accesses on a particular SBI call at read or stop or start counter, where a bunch of counters values were shared by the shared within via a shared memory between the guest and the hypervisor. So to give you more context, like how this helps, here is a, in terms of some numbers, how much traps we were able to eliminate with both ISA extensions and the software approaches. So if you look at is there a clicker? Yeah. So if you look at the first line is the baseline, what we're running. When Linux runs on the bare metal, we incur 4 traps for every context switch for every counter. So every context switch and for every counter, we have to first configure the counter, then start the counter, then stop the counter, and then unconfigure the counter at every context switch. So this would end up in, let's say you have 2 counters running, and there is 1 context switch. There would be end up in like 8 traps, which is basically an equal to M mode. And then if you are running in the virtualized mode, those e-calls happening from SBI from the guest to the host. Also, now the host has to make those e-calls down to the M mode, because host doesn't have any access of this counter way to configure. So we even end up in like 9x traps for virtualization environment. With counter delegation extensions, we reduce that to 0, because now there are no e-calls. As Beeman explained, e-call is a way to configure those counters in M mode. So we don't have any e-calls, so we reduce that to 0. For virtualization environment, we still need to make the calls from guest to the host, but we are down. We don't have to make the further call to the M mode, so we are down with 5x calls. With PMU snapshot, this doesn't matter. This doesn't change. But with additional, we are able to reduce one more set of e-calls per counter, because every counter read access now it doesn't have to trap. It has, as soon as the counters are stopped from the guest, it has a snapshot values of all the counters that's been running. So it can directly read from the shared memory without trapping. So it's kind of a virtualization mechanism to optimize the perf usage. Now, going further, for the sample collection scenario, where you are doing a perf record and you are trying to collect some samples for set of events, the number of traps. So this is additional to the context switch that's happening. This trap is the number of traps you incur only when the counter overflows and the overflow interrupt handler. There you end up in 2 plus n traps, where n is the number of counters overflown, because when you are in the overflow handler, first you have to stop all the counters, then you have to read the counters, which is additional traps that we talked about and can be optimized. But on top of that, what we do is once you want to start the counters, there are a set of counters that have overflown and there are a set of counters that didn't overflow. So the minor optimization that we put in kernel is the ones that didn't overflow can continue from the old value that's written. So it will just, we don't have to update the counter value. So it would just go and continue, start them together. And the overflown counter has to be started one by one in the bare metal case. And then for virtualization, obviously it becomes twice, because we have to make those same set of calls from S to M, like from supervisor to machine mode. So with counter delegation, we reduce that to 0, and we cut this one by half. With SBA PMU snapshot, we even reduce those counter traps that's happening in the virtualization mode, or counter read accesses. And then the only traps we're remaining is just 2, instead of 2 plus n into 2. because we just need two SPI calls. One is start the counter, stop the counter. The values that needs to be initialized are already in the shared memory between the guest and the host. Now, this is actual numbers running all these extensions in QEMU. So if you look at, I'm running a workload that has a scenario where there's a bunch of processes doing ping pong messaging. This is just to highlight the severe context switch scenario and how much overhead it can cause. So the left side is where counter delegation is enabled. You see the number of e-calls happening with the counter delegation between the previous compared to the run before and after is basically 0. So you have the same number of e-calls. But look at the right side with the SPI PMU extension in place and no counter delegation for the same workload, for the same number of processes doing ping pong messages. Look at the number of e-calls happening in that. So we saved like 15,000 e-calls for this particular workload. So the more the context switch will end up in more traps which we are able to optimize and save with counter delegation. I don't have a working the demo for the virtualization, but you'd even see more improvements when you run it on the virtualization when you run perf inside a guest. Now, so the next problem that we wanted to solve, wanted to solve in the perf area is the profiling in the blind spot area. So in kernel, there's a lot of section of the kernel runs with IRQ disabled. That means any IRQ, any interrupt cannot be delivered until that critical section where IRQ is disabled and until that critical section is finished. Now that to happen, that happens because we globally disable the interrupts in that interrupt disable path. So what do we do with the perf? Because we need to profile those critical sections as well. That's part of the code that we are running. So what we came up with is, we came up with the SBI extension called supervisor software event that allows M mode to inject event into the S mode directly, bypassing the Linux IRQ framework. And even if the interrupts are disabled, it will be able to inject those events. And this came up because there is no ISA support now for resumable NMIs in RISC-V. So we work on that with a software solution that one is reduce the interrupt latency. Second, it reduced the in general event handling path. It speeds up that one. To give you some numbers, we got 50% saved by the number of instructions executed from the point where your interrupts get generated in the hardware to the point where interrupts are actually delivered and handled in the kernel handler. So we saved almost 50% of the number of instructions that's executed in that path because we are bypassing the kernel framework. So we delivered the interrupt faster and we removed the skid when interrupts are masked. Now, so we optimized the path. We solved the counter bunch of problems with the counter delegation and other software solutions. Now we have all the counter accesses done in the S mode. But how do we tell kernel which, let's say, a vendor A, a platform A or platform B has different set of events, different set of event encodings, and different set of counters that can monitor those set of events. So how do we tell that to kernel? So with SPI PMU extension, since it was hidden by the firmware, we defined a SPI PMU device tree bindings that will tell the firmware to provide that information, and firmware can expose that to kernel via SBI calls. But that's not scalable when we have everything done in the supervisor without any assistance of the firmware. And we have also ACPI for the server, so we can't keep on adding those. So the way to way to expose this is the JSON format, which is a standard format for event encodings for perf. So that's what we adopted. But the other challenge was how do we tell which set of the events which set of the counters can be monitored by this particular event. Now, for other architectures, ARM64 allows all-to-all mapping, so you could just pick the best counter available, the next counter available for that any event. x86 does it differently, but they have limited set of microarchitecture. So based on the microarchitecture, they put basically some kind of at runtime they switches those counter mask. But for us, given RISC-V will explode in few years, have so many vendors with different encoding schemes, different constraints for those mapping, it would be best to reutilize this JSON file format. So we added one more mask, basically to indicate for this particular event, this is the counter mask that's supported. So this event, this value is being passed to the kernel, and then kernel will look for the appropriate counter from this set of counters for a particular event. And in the future, currently there is no standard events. Every other architecture has standard POF events, and there is no standard this mapping mechanism, so we have to work around in the software. Future, we are planning to have the performance event easy, which will try to define the standard PMU events and then any other standardization in this area. I think the next problem is coming back to ISA, so I'll give it back to Beeman to talk about more ISA solutions.
Back to me. Okay, so yes, the final gap we're going to talk about here anyway is the lack of control flow history. So RISC-V didn't have a way to monitor recent control flow history in a low or no overhead manner. Other architectures, x86 has LBRs, ARM has BRBE, have these capabilities that are used heavily by profile-guided optimization tools like AutoFDO, Bolt, Propeller, et cetera, that have demonstrated that they can achieve much greater gains, much greater optimizations by utilizing or collecting profiles that are enriched with this, this recent control transfer history. And so we started up a TG, earlier this year, Control Transfer Records TG. That's gone really well. We've got a spec that's stable and has been submitted already for architecture review. And so we're looking forward to having that added to our ISA options as well. Okay, so that's the list of things we've accomplished over the last, year and a half now since the SIG started. We, not the two of us, we, the community. And it's great. I'm really excited about how much we've gotten done. I think we've really made a ton of progress. We've got a long way to go still. So Atish mentioned plans for performance events TG. I think that's probably the TG that's on deck as we free up some resources from some of these other things that we've been busy on. We're also looking at sampling options for ability to perhaps sample without having to take interrupts, be able to precisely attribute samples to specific instructions, et cetera. So I foresee a TG in the future there. We're also looking at PMUs outside of the CPU. So what I call an SoC PMU, or some call an uncore PMU. So PMUs in your IOMMU, in your memory controller, et cetera. Can we look at some standardization and discovery mechanisms there? I think we'd be kind of an industry leader if we can get that done. On the software side then as well, getting the CTR support into KVM and with virtualization support, getting AutoFDO up and running now that we're going to have all of the capabilities that it needs and wants for optimizations, adding support for heterogeneous PMUs, looking at these various future ISA extensions that some of which we're talking about here. Also looking at the tools. So, we have Linux perf. There's a lot of enabling and work going on there. Some folks love that. Some prefer a tool like ARM's map or x86's vTune that is kind of an all-in-one with a GUI interface and all. Considering options there. Okay, how are we doing on time? We got about a minute. Okay, I'm not going to read through all of this. This just gives you the status of where these extensions that we've been talking about are in the process. And then similar with some of the software enabling and development that we're doing, where you can, we have links here. I assume these slides will be available somewhere after this. We flew through this. I don't know if I could have talked faster than I did. There's a longer version that has more details. If you want to learn more, we did a tech session a few months ago. You can go find that. Do we have time for a question? Well, nobody's telling me no. So, questions? Yes? So the question is, we have I mentioned an ability to sample. Can we attribute that sample to a precise IP? We don't have a standard way, no. So right now, you get an interrupt, it's up to implementations how much skid there is, and the only PC that you have is just whatever's the one, the return PC, basically, the EPC that gets recorded. But as what I mentioned with the work we want to do, looking at sampling and potentially starting a new TG, would be exactly that, of figuring out, how can we make sure that if you've got a non-speculative event, that we can tie it to the instruction that incurred that event. So that's high on our list. Right now you'll attribute the sample just to where the interrupt was taken, and so how far off that is going to be implementation dependent, but not entirely. CTR will give you the path that you took to get there, but if an implementation has the counter overflows and then you don't get the interrupt until 12 cycles later, and any number of instructions may have retired in that time, how well can you figure out which instruction caused it? Not clear. Okay, question in the back. In terms of like percent improvement or something? Do you have insights on that?
So we don't have, for the ISA extension, those are new. So I don't think we have any hardware that's available. You're talking about the hardware performance, not the QEMU numbers, right? Yeah, so for the hardware ISA extensions, we don't have any hardware that's available. For the software, yeah, we could done that. The performance numbers I showed is all QEMU or Spike, but technically we could run those on any hardware that's available today with countered SCOP PMF and then get some better numbers. We are trying to do that for the blind spot one and then get to see how fast we can get to the perf event, but we won't save much on trap because the major trap saving happens when we have counter delegation, which is not available in any of the existing hardware that's out there.
Okay, I would imagine we're out of time, so thank you very much.